What happened in the first moment of the universe, when time had not yet taken a breath, and light did not know its own name? That question has haunted humanity like a small flame burning quietly in the dark. Today, we will unveil that primordial curtain and touch the first seconds after the Big Bang, where the universe trembled like a newborn being. Leave a comment. Share your intuition, for perhaps your feeling is the missing piece. And now, step into the moment when the first light arose. What if the first light of the universe was not a blinding explosion at all, but a shy awakening, a soft inhale in the darkness where time itself was still learning how to move? In that unimaginably brief instant after the Big Bang, perhaps around 10 to the power of minus 36 seconds, the cosmos was not yet a sky of stars. It was a storm of pure energy, a sea of boiling fields where space and matter were still tangled together like threads in a loom that had just begun to turn. Physicists tell us that in that first fraction of a heartbeat, the universe expanded faster than any imagination, stretching from smaller than a particle to vast beyond comprehension in what we call cosmic inflation. Alan Guth once suggested that the universe is perhaps the ultimate free lunch, born from a tiny fluctuation that swelled into everything we see. In that churning brightness, temperature and density were so extreme that nothing resembling an atom could exist yet. Only a wild dance of quanta, particles and antiparticles flashing in and out of existence like thoughts in a fever dream. If you could stand there as a silent witness, you would not see stars or galaxies. You would be submerged in a blinding ocean of light that could not yet travel freely. Photons constantly scattered by charged particles trapped the way sound is trapped inside a thundercloud. Stephen Hawking once reflected that understanding the universe at its beginning is like knowing the mind of God, not as a doctrine, but as a way of saying that these first instants carry the blueprint of all that will follow. In that sense, the first light is not just a flash. It is a promise, the seed of every sunrise that would ever shine on any world. As the universe expands, it cools. And in that cooling there is a kind of cosmic compassion, a gentleness arriving after fury. The dense plasma relaxes, particles slow enough to begin forming the first simple atoms of hydrogen and helium. Carl Sagan spoke of us as star stuff, contemplating the stars. Yet even before stars, there was this tender moment when matter first learned to hold itself together, when light, for the first time, could slip free and travel through space without being immediately swallowed again by chaos. Hundreds of thousands of years after that first instant, the fog finally thinned, and the ancient light broke loose. Today we still receive it as the cosmic microwave background, a faint afterglow bathing all of space. Roger Penrose has called this glow a kind of fossil of the early universe, a preserved imprint of that young, hot cosmos. When scientists map this relic light, they see tiny ripples in temperature and density, the first fingerprints of structure, the earliest hints of where galaxies would one day form. So when we speak of the first light rising, we are not only describing photons escaping a cosmic storm, we are also describing the first sketch of destiny. In those ripples are the future locations of clusters and voids, of stars and planets, of every place where eyes would open and ask why. The universe was still almost perfectly smooth, yet not completely so. And that tiny imperfection is the reason you exist to listen now. A perfectly smooth universe would have had no stars, no worlds, no one to wonder about, beginnings. From a personal point of view, I find this deeply humbling. We often imagine power as violence, as thunder and collision. But the true power of the cosmos lies in its patience, in the way it allows small differences to grow slowly into galaxies and into lives. Out of an inferno so violent that even language breaks trying to describe it, emerged a universe capable of quiet lakes, forests at dusk, and human hearts that ache when they look at the stars. The first light was not only an event in physics, it was the first note in a long symphony of meaning. The lesson that rises from this story is simple yet profound. From chaos can grow harmony. From noise can grow pattern. From a moment where nothing is stable can emerge a cosmos that writes poems with atoms and memories with neurons. When you feel small, remember that your thoughts are woven from the same light that once fought to escape the newborn universe. The same light that has been traveling for billions of years just to arrive gently at the back of your eyes tonight. If this slow journey through the first light of creation soothes something inside you, let that be a quiet signal, a reminder that you are part of this story too. And if you wish this story to continue, if you want more nights where science becomes a soft pillow for the mind, you can support this fragile stream of curiosity with a gentle like and a calm subscription, almost like placing another small star in a dark sky. Your comment, your question, your doubt, they all become tiny ripples in this shared universe of thought. As we drift together on this river of time, let us carry one image forward. A universe newborn, hot and crowded and wild, slowly learning how to let its first light breathe. In the next step of our journey, we will follow that light as it stretches across the growing cosmos, as it guides the birth of stars and the weaving of galaxies, as it turns emptiness into a cathedral of fire. For now, close your eyes for a moment and imagine it. The hush before the stars, the sacred instant when the first light rises. Asterisk. What if there was a moment when the universe swelled like a mirage trembling above hot desert sand? When time had barely learned to breathe, and light was still nameless. The era of inflation invites us into that forbidden instant, a fraction of a heartbeat after the Big Bang, when space-time itself unfurled faster than any photon could chase. It is a question that pulls at the mind the way distant starlight pulls at the eye. Delicate, ancient, irresistible. Physicists describe inflation as a cosmic blooming, a sudden flowering of space where the universe expanded from smaller than an atomic nucleus to astronomical scales in less than a blink. Imagine holding a speck of dust between your fingers, then watching it swell into the size of a galaxy cluster. Not because matter is rushing outward, but because the fabric beneath it is stretching in every direction. Alan Guth once said that inflation was the moment the universe borrowed energy from the vacuum to write its own story. That poetic boldness captures the spirit of the idea. The notion that space is not a passive background but a living field capable of driving its own expansion. The strange energy responsible for inflation is not matter, not radiation, but something subtler, a field woven through the void itself. In one of those paradoxes only the cosmos would dare attempt. This energy did not pull or collapse. It repelled, turning space into a runaway ballooning experiment. Stephen Hawking described the early universe as a storm of tiny quantum fluctuations, jittering unpredictably at microscopic scales. Inflation took those fluctuations and magnified them across trillions of miles, freezing them into the seeds of future galaxies. In a deep sense, the grand cosmic web we map today is nothing more than magnified quantum whispers. When satellites like COBE, WMAP and Planck mapped the cosmic microwave background, the oldest light we can see, they revealed an astonishing truth. The universe at a young age was nearly the same temperature everywhere, differing by only 1 part in 100,000. Without inflation, this uniformity would be impossible. Distant regions would never have had time to exchange information, not even at light speed. Yet the smoothness was there, waiting, serene as a freshly laid field of snow. Those faint temperature ripples are the fingerprints of inflation, the frozen memory of that brief but world-shaping expansion. André Linde likened the inflating universe to a self-reproducing fractal, endlessly budding and blooming. In some models, inflation never entirely ends. It merely slows in pockets, each pocket becoming its own universe with its own story. These ideas verge on the mythic, yet they remain grounded in mathematics and observation. Letting your mind drift into this early epoch is like sinking slowly into warm cosmic water, the boundaries between science and poetry dissolving like mist. You may imagine the primordial universe as a giant breathing lung, inhaling possibility, exhaling space. The galaxies we see today, the clusters and voids, the delicate lattice of dark matter, all ride upon that ancient breath. Quantum foam becomes filaments. Filaments become rivers of matter. Rivers become constellations of worlds. A single jitter in the fiber vacuum becomes a supercluster of galaxies. The same way, a single grain of sand becomes the anchor of an entire pearl. The soothing part of this tale is its unity. The idea that the rules governing the tiniest particles also sculpted the largest structures ever to exist. If you listen closely, it is almost musical. The universe begins with a single high note, sharp, impossibly brief. And that note stretches, deepens, blossoms into the vast cosmic chord we inhabit now. Inflation also explains why space is so incredibly flat, like a sheet pulled tight across infinity. Without it, the curvature of the universe could have been wildly chaotic. Instead, our cosmic horizon behaves like a disk brushed smooth by an invisible hand. But science is never so simple, and inflation is not a final answer. Some physicists argue that its simplicity is deceptive, that the universe may be hiding even stranger beginnings. Others search for primordial gravitational waves, faint ripples in space-time that inflation should have produced. Finding them would be like hearing the infant heartbeat of creation itself, a lullaby from the first fraction of a second. Still, the evidence we do have aligns with uncanny precision. The distribution of galaxy clusters, the shape of the cosmic microwave background, the nearly flat geometry of space, all whisper the same story. Inflation was the silent sculptor of the early universe. As you drift deeper into this narrative, you might imagine space-time as a soft fabric under your fingertips, gently trembling with ancient vibrations. The edges of reality blur, and the distance between now and the beginning becomes almost touchable. Let your breathing slow. Let your thoughts loosen. Let the early universe rise before you like a dream half remembered. It is calming to think that everything familiar, the warmth of the sun, the quiet of midnight, the pull of gravity, the blue glow of Earth emerges from one impossible instant. An instant when the universe stretched itself into being, as if awakening from nothingness. Inflation is not merely an idea. It is a lens through which we see the continuity between the smallest tremors of quantum fields and the largest arcs of galaxies. It is the bridge that binds the unimaginably tiny to the unfathomably vast. If the theory is correct, then the cosmos we observe is only one bubble in a much larger sea, drifting gently in a foam of possibilities. Yet our bubble, with its stars and moons and fragile beings who ask questions, is precious enough. The early universe did not roar. It bloomed. It did not surge outward like an explosion. It unfolded like a flower opening in the dark. It did not race away from itself. It breathed itself into expansion. And now, as your mind hovers in that soft threshold between thought and sleep, imagine the moment when inflation ended, when the wild expansion softened, cooled, settled. In that stillness, the first photons were born, the first whispers of light that would one day become the cosmic microwave background. From the mirage of inflation, light finally emerged, trembling, newborn. And so, as our journey continues, we follow that newborn glow, stepping gently into the next great mystery. The moment when the first light arose. What did the universe feel like in the instant when the first particles were born from a roaring sea of pure energy? Imagine not stars, not atoms, not even light as we know it, but a blinding ocean where existence itself is still deciding what it wants to become. In that unfathomably early moment after the Big Bang, everything is so hot and so dense that matter cannot yet settle into familiar forms. It is a storm of possibilities, a cosmic cauldron where quark, gluon, electron and neutrino dance in a violent yet strangely beautiful chaos. If you could float there with a calm mind, you would not see solid objects, only a radiant fog of energy, vibrating and colliding in every direction at once. Physicists call this the quark-gluon plasma, a state so extreme that even the building blocks of protons and neutrons refuse to stay bound together. It is as if nature herself is still trying out shapes, tasting each configuration before allowing anything stable to exist. In this ocean, the temperature is trillions of degrees, so intense that words like hot or bright collapse under the weight of reality. Our language is too small for such a storm. Richard Feynman once said that to truly understand a thing is to be able to imagine it simply. Yet here, simplicity escapes us. We are forced to rely on equations and particle accelerators, on detectors buried underground or frozen in Antarctic ice, to glimpse echoes of that first incandescent moment. And still, like monks listening to distant bells in the mist, we close our eyes and try to see with the mind what the eyes can never witness. In that primordial sea, quark and gluon are not quiet. They are restless children running through a crowded cosmic marketplace, constantly colliding, breaking apart, reforming. Gluon carry the strong force, the invisible thread that will one day knit quark together into proton and neutron. But in this early era, the thread is not yet woven into fabric. It is just bright strands whipping wildly through the dark. Electrons move like sparks at the edge of a bonfire, sometimes captured for a breath of cosmic time, sometimes flying free again. Neutrinos, those ghost-like travelers, slip through everything almost without touching, already preparing for their destiny as messengers from the deep past. Stephen Hawking once reflected that we are trying to understand the mind of God when we study the laws of the universe. In this early epoch, those laws are not gentle. They are carved in lightning. Space itself is expanding at a furious rate, stretching this churning sea so quickly that regions once in contact lose the chance to speak to each other again. Yet somehow, from this frenzy, patterns begin to whisper into existence. Tiny fluctuations in density, little ripples where energy is slightly more or slightly less than average, drift through the plasma like soft breaths in a sleeping giant. Those ripples will one day become galaxies, clusters, entire webs of cosmic structure. But, for now, they are only hints, seeds carried by the turbulent wind of the newborn universe. Sean Carroll has described the early universe as simple in content yet profound in implication. Almost everything is the same everywhere, yet hidden in that sameness are the clues that will decide the fate of stars and life. This is the paradox of the primordial sea. It is both uniform and pregnant with asymmetry. Matter and antimatter are created in pairs, equal and opposite, like twin reflections on a still lake. In principle, they should annihilate perfectly, leaving behind only light. And yet, something tilts the balance ever so slightly, leaving a tiny surplus of matter over antimatter. That tiny unfairness, that subtle breaking of symmetry, is the reason you exist to ponder it at all. As Andrei Sakharov argued, without such a symmetry there would be no galaxies, no stars, no observers to ask questions. So in that sea of energy, perhaps the universe makes its first moral choice, not between good and evil, but between perfect balance and the possibility of story. Perfect balance would have meant silence, a cosmos of pure radiation with nothing to remember. The slight imbalance gives rise to atoms, chemistry, consciousness. It is as if the universe gently leans toward narrative, toward the chance that one day some small being on a small world will look back and ask how it all began. In heavy ion colliders on Earth, like those at CERN and Brookhaven, we attempt a kind of modest alchemy. By smashing nuclei together at extreme energies, we recreate droplets of that ancient quark gluon plasma, fleeting suns contained within magnetic bottles. Detectors record the spray of particles, and from their paths we reconstruct the behavior of a universe no human eye has ever seen. One experimenter described this as reading the diary of the universe written in its own handwriting, a script of tracks and flashes rather than ink. When the droplets cool, quark begin to bind, like dancers finally locking hands after a wild improvisation. Proton and neutron emerge, and with them, the possibility of stable matter. This cooling is not just a change in temperature, it is a phase transition in being itself. The universe moves from pure becoming to the first hints of being, from formless energy to recognizable structure. Imagine listening to an orchestra tuning, each instrument playing random notes, noise without theme. Then, slowly, the tones begin to align. A chord appears. A melody takes shape. The primordial sea is that tuning phase, and the emergence of particles is the first tentative chord of cosmic music. Some cosmologists, like George Smoot, have called the fluctuations in the early universe the handwriting of God, not as doctrine, but as a way to express awe at their significance. Those minute variations, etched into the plasma and later frozen into the cosmic microwave background, are our oldest map. They tell us that even when everything seemed uniform, the seeds of difference were already there, waiting to bloom into stars and worlds. In a meditative sense, this early universe mirrors the mind. At first, our thoughts are chaotic, a rushing plasma of fears, hopes, memories. With practice, with stillness, patterns emerge, alignment appears. Just as the cosmic sea cooled and allowed particles to form, our inner storms can cool, letting stable insights crystallize. The physics is relentless, governed by equations of quantum fields and general relativity. Yet within that relentlessness there is something strangely gentle, a patient unfolding over billions of years from plasma to planets, from particles to persons. The fact that quark and gluon once roared in a state beyond imagination does not distance us from them. It binds us more intimately to the cosmos. Every atom in your body was once part of that first sea of fire. Every neuron that now forms a thought was forged from matter that learned to cool, to combine, to endure. When you close your eyes at night and listen to the quiet, you are not separate from that ocean. You are a wave that has risen from it for a brief moment, aware of itself. So, as we speak of quark, gluon, electron, and neutrino, we are not reciting cold catalogues. We are telling a love story between energy and form, between chaos and coherence. The primordial sea may seem distant in time, yet it is present in every breath, because the air you breathe, the blood that flows, the photons that touch your eyes all descend from that first incandescent moment. And as this tale of fire and particles gently settles in your mind, like stardust finding a resting place, the story is already flowing toward its next chapter. From the seething plasma to the birth of light, from the ocean of energy to the moment when the universe first learned to shine. What really happened in the first fragile heartbeat of reality when matter somehow won and antimatter lost? Why do you exist here and now, listening to this voice, instead of dissolving back into perfect cosmic balance? Physicists call it the matter-antimatter asymmetry, a phrase that sounds dry and technical. Yet underneath it is the most intimate of all questions. The question of why there is something rather than nothing. If in those first instants after the Big Bang matter and antimatter had been created in exactly equal amounts, they would have met each other like twin lovers rushing into an embrace, only to annihilate in a pure flash of light, leaving a universe made only of radiation, no stars, no planets, no oceans, no memories, no you. And yet that is not the universe we see when we look up at the night sky. Somewhere in that infant chaos, a tiny preference appeared, a whisper of bias toward matter over antimatter. Out of every billion pairs of particles, one lonely extra matter particle survived the cosmic storm. And from that almost invisible excess, all the galaxies and all the stories were born. The Russian physicist Andrei Sakharov once suggested that the universe must have broken its own perfect symmetry to allow this to happen. He imagined the early cosmos as a kind of laboratory furnace, unimaginably hot, where fundamental processes slightly favored matter. Like a dealer at a cosmic table, who lets just one extra chip slide to one side. We call this baryogenesis, the birth of more baryons matter than antibaryons antimatter. It is not a single event but a melody of conditions that had to be met all at once. Interactions that treat particles differently from antiparticles. A universe out of thermal equilibrium, and the breaking of certain delicate symmetries that nature usually guards with jealous care. In the quiet of a dark room, if you close your eyes and breathe with the slow rhythm of the cosmos, you can almost imagine that furnace. Space not yet transparent. Time not yet measured in seconds, only in phases of expansion. Everywhere, pairs of particles and antiparticles appear out of the seething vacuum, collide, and vanish back into light. This dance is fair and impartial, an endless tide that gives and takes in equal measure. Yet somewhere in the equations describing these processes, there is a small asymmetry in how the laws treat one direction of time versus its reverse. One electrical charge pattern versus its mirror image. Physicists call it CP violation. James Cronin, who helped discover such violations in the decays of neutral K mesons, once reflected that these tiny deviations from symmetry may be the reason we are here at all. Another thinker, Steven Weinberg, mused that the very fact of our existence is already a kind of clue. A message from the early universe that the laws of physics allowed, perhaps even demanded, an imbalance. In a poetic sense, the universe cheated in our favor, and history has been the slow unfolding of that original unfairness. Imagine now those first microseconds as a stormy ocean of quark-gluon plasma. Quarks and antiquarks churned together with gluons, the carriers of the strong force. Everything is so hot that no protons or neutrons can yet exist. Only a fluid of elementary ingredients. In this ocean, the rules governing particle interactions are slightly skewed, so that in certain reactions matter is produced just a fraction more often than antimatter. It is not dramatic. There is no thunderclap announcing the victory of matter. It is more like a slow, patient leaning of the scales. Over and over the universe throws dice, and every billion throws or so, matter wins by one. As the cosmos expands, it cools. The quark sea condenses into protons and neutrons, and their antipartners. The vast majority still annihilate each other, flooding the universe with a bath of high-energy photons. But that small excess created by baryogenesis cannot find partners to cancel with. They remain as a ghostly residue. Those are the particles that will one day assemble into the cores of stars, the stones of planets, the calcium in your bones. You are, in the most literal sense, made of the leftovers of an ancient war that almost ended in perfect mutual destruction. Richard Feynman once joked that antimatter is just matter going backward in time. In the early universe, you could say that past and future themselves were competing. One direction, slightly preferred over the other. That preference echoes today in the arrow of time we feel when we watch a glass fall and shatter but never spontaneously reassemble. The same deep asymmetry that gave matter a slight edge over antimatter also seems linked to the way entropy increases, the way memories form in only one direction, the way your life flows from childhood to old age, and not the reverse. When cosmologists simulate this epoch on supercomputers, they watch as a uniform field of energy transforms into particles, as interactions governed by the standard model and its possible extensions sculpt the delicate difference between matter and antimatter. Yet even today our theories are incomplete. The known sources of CP violation in quark physics do not seem large enough to account for all the matter we see. Some suspect that new physics hides in the behavior of neutrinos, those shy, almost massless particles that flood the cosmos. Others imagine exotic fields or heavy particles that decayed asymmetrically in the first instant. Here the story becomes almost mystical. For in trying to understand why matter triumphed, we are also asking whether the laws of nature are fixed and final, or part of a deeper pattern we have only begun to glimpse. Are we the inevitable outcome of these laws, written into the fabric of the vacuum from the start? Or are we a lucky accident, a brief flare in an indifferent multiverse where most regions ended as empty seas of light? Some thinkers like Alexander Vilenkin speak of eternal inflation creating countless bubble universes, each with its own parameters. In most of them, perhaps matter and antimatter truly cancel perfectly. And only, in rare pockets, does an asymmetry appear and life awaken to wonder at its own improbable birth. As you listen, perhaps lying in the dark with eyes half closed, let this idea settle upon you like stardust. Every atom in your body is a survivor, a veteran of that primal annihilation. When you rest your hand on your chest and feel your heartbeat, you are feeling the rhythm of matter that refused to vanish, that carried forward through billions of years of cosmic evolution. Galaxies swirling, stars igniting and dying, heavy elements forged in, supernovae and neutron star mergers. All of that begins with an almost imperceptible tilt in the early balance between matter and antimatter. There is a quiet humility that comes with this understanding. On one hand, we are not separate from the universe at all. We are simply what happens when a field of energy chooses not to remain symmetric. On the other hand, we are astonishingly rare. The visible matter in the cosmos is only a small fraction of its total content. Most of it is dark matter and dark energy that do not shine and barely interact. That means the portion that forms stars and people is a minority twice over. First, for being matter instead of antimatter. Second, for being luminous instead of dark. When you hear a physicist say that for every billion pairs of matter and antimatter there was one extra matter particle left behind, you might imagine a vast cosmic lottery. The ticket with your name on it was printed in that moment, not with ink, but with the value of certain constants and the behavior of certain interactions. If any of them had been slightly different, there might have been no asymmetry, or too much. No structures at all, or perhaps a violent clutter of matter overwhelming the delicate stability needed for chemistry and life. The universe we inhabit is balanced on a thin ridge between nothingness and chaos. In the soft twilight between waking and sleep, this story can feel less like a scientific explanation and more like a meditation on gratitude. Gratitude not in a religious sense, but in a cosmic one. Gratitude that the vacuum allowed this small rebellion against symmetry. That time chose a direction. That matter gained a sliver of advantage. As the astrophysicist Carl Sagan once reminded us, we are a way for the cosmos to know itself. Here that phrase takes on new depth. For we are not merely made of star stuff. We are made of asymmetric stuff, of the fraction that stayed when everything else cancelled out. So the next time you look into the dark between the stars, remember that you are looking at both the evidence of annihilation and the triumph of survival. The darkness carries the relic glow of all those pairs that vanished. A sea of photons now cooled into the cosmic microwave background. The points of light are the rare archipelagos of matter that endured, clumping under gravity to become suns, worlds, and eyes that can gaze back in wonder. And as you drift slowly towards sleep, let a final question follow you into your dreams. If the universe once chose matter over antimatter by the smallest of margins, what quiet choices are you making now in your own brief corner of space-time? What tiny asymmetries of kindness and curiosity might ripple outward across the long future that still lies ahead? What would it feel like to awaken in a universe where light exists yet cannot escape? Imagine opening your eyes into a cosmos that is not dark in the way night is dark, but dark in the way a storm cloud is dark from the inside. Everywhere around you a blinding brightness that never becomes vision. Only a suffocating glow trapped in its own prison of matter. For the first few 100,000 years after the Big Bang, that was the true face of our universe. A sea of plasma, a fog of charged particles, and scattered photons, stretching in every direction with no stars, no galaxies, no clear line of sight for light to travel freely. When we say plasma fog lasting about 380,000 years, the words sound almost gentle. But this was a time when the entire universe was so hot that atoms could not exist as we know them. Protons and electrons were torn apart by the intense energy, leaving behind an electrically charged soup where particles and light were constantly colliding. Every photon that tried to move in a straight line was almost instantly scattered by a free electron, forced to change direction again and again. The path of light became a frantic random walk, a cosmic game of pinball played at unimaginable temperatures. From a distance, if there had been any observers then, the universe would not have looked like the transparent space we know today. It would have been more like being inside a dense cloud on a mountain night, where every beam from your flashlight is swallowed within a few steps. In such a fog, you do not see shapes, only the brightness of the mist itself. That is why cosmologists say that before this fog lifted, the universe was opaque. Light was not absent, it was trapped. At a deep physical level, the reason light could not escape lies in the intimate link between radiation and matter in those first ages. The density of particles was enormous, far beyond anything we can recreate on Earth, except for brief moments in powerful experiments. In that density, the typical distance a photon could travel before hitting an electron was extremely small. We call that distance the mean, free path. And in the early universe it was so tiny that light had no chance to propagate across cosmic scales. So the universe was full of light, yet nothing could see anything. It was as if creation had pressed a pause button on transparency. The information carried by these photons, the tiny variations in density, the seeds of future galaxies, were already encoded in that glowing plasma. But they were locked away, waiting for the cosmos to cool just enough for a transformation to occur. That transformation is one of the most beautiful moments in the entire history of reality. After roughly 380,000 years, the universe had expanded and cooled to a temperature at which protons and electrons could finally combine to form neutral hydrogen atoms. When that happened, the fog began to thin. Neutral atoms do not scatter light in the same violent, constant way free electrons do. Suddenly the mean free path of photons became enormous. Light that had been bumping helplessly from one particle to another was finally released to travel in straight lines across the growing cosmos. Cosmologists call this moment recombination or decoupling. But those technical words hide the quiet poetry of what really happened. A universe that had been glowing inside itself like an overcast sky finally became transparent. The fog lifted, and the very first light that could truly escape began its journey through space. That ancient radiation has been traveling ever since, stretching with the expansion of the universe. And today we observe it as the cosmic microwave background. When the Nobel laureate George Smoot described the first detailed map of this background, he said it was like seeing the face of the young universe for the first time. In those faint temperature ripples, just 1 part in 100,000. We are looking at the fossil imprint of that once impenetrable plasma fog. Each tiny patch of slightly hotter or cooler glow corresponds to regions where matter was just a little denser or thinner. Over billions of years, those differences would grow under gravity into galaxies, clusters, and the grand cosmic web. Jim Peebles, another giant of modern cosmology, once reflected that studying this background light turns cosmology from speculation into a precise science. In other words, by listening to the faint after echo of that plasma fog, humanity has moved from myth into measurement. We are no longer just telling stories about creation, we are reading its actual light. If you imagine this as the opening hook of a story you tell your audience, then the phrase plasma fog and a darkness lasting 380,000 years is not just a dramatic metaphor. It is an invitation to step inside a time when the universe was young, hot, and blinded by its own brilliance. The curiosity you awaken is simple yet profound. How can a universe be full of light and yet remain dark? As you unfold the explanation, you guide the listener gently through scales they cannot see. You show them photons bouncing like restless fireflies trapped in a glass sphere. You let them feel the claustrophobia of a cosmos where every direction is crowded with particles. You explain that for light to truly illuminate, it must travel. It must carry information from one place to another. In the plasma age, that journey was impossible. Then, slowly, almost like a meditation, you guide them toward the turning point. The universe breathes out, expanding, cooling. Temperatures fall. Collisions become less violent. Protons and electrons find each other and settle into delicate orbits, becoming neutral atoms. In that quieting, scattering decreases, and the fog begins to clear. Max Tegmark has poetically called the cosmic background light our baby picture of the universe. It is a photograph taken not with a camera, but with physics itself. Every time we observe it, we are looking back to the exact moment when the plasma fog dissolved and the cosmos took its first clear breath of transparency. There is something deeply meditative in this story. For most of its infancy, the universe was not yet ready to be seen. It was still forming its structures, still smoothing out its violent beginnings, wrapped in a shimmering cocoon of plasma. Only when it had cooled, calmed, and recombined did it allow its inner pattern to emerge in light. In a way, the cosmos practiced its own kind of patience. When you tell this tale in a slow, warm voice, as if drifting through space with the listener, the physics becomes more than equations. It becomes a mirror for our own lives. How many times do we move through periods where everything feels like fog, where information and emotion collide too quickly, where no clear path of understanding can be seen? Only after some cooling, some expansion, some time, do patterns emerge, and the light of insight finally travels freely through the mind. Stephen Hawking once remarked that the fact we can understand the universe at all is itself a kind of miracle. Here, in the story of the plasma fog, that miracle is especially vivid. Creatures who evolved in one tiny corner of a late-forming galaxy now reconstruct conditions from a time when no galaxies existed, using the faint glow of light that has been traveling for nearly 14 billion years. So when your video opens with the image of a universe drowned in plasma mist for 380,000 years, you are not just setting up a scientific explanation. You are inviting the listener to lie back, close their eyes, and drift backward to an age before stars, before planets, before any structure we would recognize. You are asking them to imagine being present at the moment when darkness was not the absence of light, but the overwhelming presence of it, trapped and unable to speak. In that gentle darkness, with your voice as a guide, science becomes a kind of cosmic lullaby. Each explanation about scattering and recombination is also a verse in a larger song about how clarity emerges from chaos, how transparency follows opacity, how light eventually finds a way to leave the fog and reveal the universe to itself. And perhaps the most beautiful question to leave hanging in that quiet space is this: if the universe once hid all its light inside a fog of plasma, how many other truths are still wrapped in veils we have not yet learned to lift? What if the oldest light in the universe is not just a relic of violence but a soft lullaby still echoing around you right now? Imagine you are floating in a dark cosmic ocean, eyes closed, breath slow, and rut far beneath all galaxies and stars. There is a faint background glow that has been singing since the universe was a baby. We call it the cosmic microwave background, CMB. But the name is dry compared to what it really is. It is the first light that ever truly got free, the oldest photograph of reality, the afterglow of creation itself. There was a time when no light could travel anywhere at all. In those early hundreds of thousands of years after the Big Bang, the universe was not full of stars or galaxies. It was full of a blinding fog of charged particles and radiation. Protons and electrons were too hot and energetic to settle down into atoms. They danced wildly in a plasma that scattered every photon like raindrops in a thunderstorm scatter headlights on a wet road at night. Light tried to move in straight lines, but it could not take even a tiny step without being thrown off course by some restless particle. The cosmos was bright, yet strangely opaque, glowing yet unable to see itself. Slowly, as the universe expanded, it cooled. Temperatures dropped from unimaginable fire down toward a gentler warmth, until finally, about 380,000 years after the beginning, something extraordinary and very quiet happened. Protons and electrons began to find each other and stay together. The first neutral hydrogen atoms were born, simple and fragile, like the first snowflakes settling after a storm. When that happened, light no longer bounced off every charged particle in its path. The fog thinned, the universe became transparent, and the photons finally slipped free into the darkness. Those same photons have been traveling ever since, stretched by expansion, cooled by time, and now they bathe all of space in a faint microwave glow. This is the cosmic microwave background, the oldest light we can see, a soft relic from when the universe changed from chaos into clarity. The physicist Stephen Hawking once remarked that the CMB is like a message from the very early universe written in light. Others have called it the baby picture of the cosmos, the moment when the universe first became visible to itself. When you look at a map of the CMB, you are not seeing stars or galaxies. You are seeing the temperature of space at that ancient moment when atoms first formed and light first went free. For a long time, this light was only a theoretical whisper in the equations of cosmologists. Then, in the 1960s, two radio engineers, Arno Penzias and Robert Wilson, found a mysterious noise in their antenna. It came from every direction, day and night, through every attempt at cleaning and correction. At first they thought it was interference, even pigeon droppings in the equipment. But the noise remained, calm and uniform, like a background breath woven into the fabric of the sky. Only then did they realize, with the help of theorists, that they had stumbled onto the fossil radiation of the early universe. The quiet hiss was not a mistake. It was the voice of creation settling into silence. Decades later, satellites like COBE, WMAP, and Planck would map this background light with astonishing precision. The cosmologist George Smoot once said that seeing the first detailed CMB maps was like looking at the face of God. Not as a religious claim, but as a way of expressing the awe of watching the universe reveal its infant features. On those maps, the sky is not perfectly smooth. It is mottled with tiny variations in temperature. These small ripples encode the seeds of all future structure, the faint differences that gravity would later amplify into galaxies, clusters, and eventually into the very stars and planets that cradle your existence. When you listen carefully to what this ancient light is telling us, a whole story unfolds. The overall uniformity of the CMB says the early universe was remarkably smooth, the same in every direction on large scales. At the same time, the tiny irregularities say that quantum fluctuations, microscopic jitters in the fabric of reality, were stretched to cosmic size during a brief period of rapid expansion we call inflation. The cosmologist Jim Peebles has often emphasized that without those tiny differences, there would be no galaxies, no stars, no life. The CMB shows us both our insignificance and our necessity. We are the outcome of fluctuations written in that first light. There is something deeply meditative in this knowledge. As you sit, perhaps in a quiet room, perhaps late at night with the world around you dimmed, the CMB is still there, above you and through you. Every bit of empty space in the room is filled with these ancient photons, drifting gently at a temperature only a few degrees above absolute zero. They wash through your body, through the walls, through the earth itself, indifferent yet constant. You do not feel them, but they are part of the cosmic climate you inhabit. To breathe slowly in such a moment is to breathe in a universe that once glowed like a furnace and now dreams in microwaves. Think of those first atoms forming, hydrogen and a little helium, simple notes in a vast unfinished symphony. With atoms came transparency. With transparency came the first true distance, the first separation between things. Light could finally travel without being scattered at every step. and so the universe gained memory. The CMB is that memory made visible, a snapshot preserved in the most subtle of colors and temperatures. Every measurement we make of it helps us refine the age of the universe, its composition, its curvature, its ultimate fate. Scientists sometimes speak very practically about all this. They say that the CMB confirms the Big Bang model, that its spectrum is an almost perfect blackbody, that its tiny anisotropies match predictions from inflationary cosmology. All of that is true, and it is a triumph of human reasoning. Yet, beneath the equations, something softer is happening. A species that evolved on a small rocky world around an ordinary star has learned to read the faint afterglow of an event older than any star, older than any galaxy. We have taught ourselves to listen to the universe talking about its childhood. If you let the facts slow down in your mind, the feeling changes. This is no longer only a story of particles decoupling and photons redshifting. It is a story of emergence. From a hot, opaque ocean where nothing could be seen, a transparent cosmos unfolded. From formless plasma, simple atoms. From simple atoms, complex chemistry. From complex chemistry, stars and planets. From stars and planets, eventually, you. The CMB marks the first moment when the universe opened its eyes, even though it would take billions of years before any living mind would look back and understand what that meant. So when we say that the cosmic microwave background is a reliable imprint of the time just after the Big Bang, we are also saying something more intimate. We are saying that the universe has kept a record of its first transition from blindness to sight. And that record is written in the very light that now passes silently through your life. The next time you lie under the night sky, watching stars that are already old, remember that there is an even older glow behind them all. It is not bright enough for your eyes, but your mind can feel it. In that sense, meditating on the CMB is like meditating on your own earliest memory. Blurred, incomplete, yet incredibly precious. This is the universe as an infant, wrapped in a blanket of light. We now know that this blanket exists, that it has a precise temperature, that its tiny patterns seeded everything that would follow. But knowing in the scientific sense is only half the story. The other half is sitting quietly with that knowledge, feeling the slow expansion of time around you, and realizing that the oldest light in existence is still here, still singing, still holding the memory of when atoms first formed and the universe first learned how to let light go free. What happened in the first moment of the universe, when time had not yet taken a breath, and light did not know its own name? That question has haunted humanity like a small flame burning quietly in the dark. Today, we drift back into that primordial silence, to a time before galaxies, before planets, before even the idea of structure existed. The universe had expanded and cooled since the Big Bang, leaving behind a vast neutral fog of hydrogen stretching endlessly in every direction. This was the age we call the cosmic dark ages, not for lack of motion, but for lack of a single flame to break the night. Yet in that stillness, tiny ripples seeded in the first heartbeat of creation began to grow under gravity. In some regions the gas was just slightly heavier, slightly more patient, and like dew forming on invisible threads of dark matter, it began to fall inward. Clouds collapsed, heated, spun, and tightened until the pressure at their hearts forced nuclei to fuse. At that delicate balance of gravity and fire, the first stars were born. Astronomers call them Population 3, the universe's first attempt at building suns, because they formed from pristine gas containing no heavy elements. They grew enormous before igniting, some hundreds of times the mass of our sun. These were not gentle stars. They were roaring furnaces that lived fast, burned violently, and died young. Their intense ultraviolet light did something transformative. It stripped electrons from hydrogen atoms around them, turning the neutral fog into a glowing plasma once again. Bubble by bubble, the universe began to clear, and the cosmic night softened. This slow unveiling is what we call reionization, the great lifting of the universal veil. It did not happen all at once, but like the first colors before dawn, spreading quietly across the sky. In one region, a cluster of massive stars erupted in light, then another, until their glowing bubbles merged into an expanding web of transparency. Over hundreds of millions of years, the universe shifted from dark and neutral to clear and luminous. Inside their massive cores, these stars forged the first heavy elements: the calcium in our bones, the oxygen we breathe, the iron carried quietly in our blood. Many Population 3 stars ended in cataclysmic explosions so powerful that they left behind no remnant, only expanding shells of enriched gas. As these shock waves swept through surrounding clouds, they seeded the universe with material that could cool more efficiently, enabling smaller, longer-lived stars to arise. In those later generations, planets could form, chemistry could flourish, and life could someday wonder how all this began. Physicists often say that we are made of stardust, but the truth runs deeper. We are not just made of stars. We are made of the second generation of stars, which themselves were made possible only by the violent generosity of the first. Population 3 stars did not survive, yet their fingerprints remain in every atom of our bodies. When you lift your hand toward the night sky, you are raising the ashes of forgotten suns back toward the womb that created them. We have never seen a Population 3 star directly. Their lives were too brief, their deaths too complete. Instead, we trace their existence through faint chemical signatures in ancient stars, through the transparency of intergalactic space, through the earliest galaxies whose light reaches us after more than 13 billion years. It is like listening for the first songs ever sung by studying their echo in a distant valley. The story of these stars is not merely a chapter in astrophysics. It is a chapter in our own becoming. Without them, there would be no carbon, no oceans, no trees, no breath. They lit the first lamps in the universe, cleared the fog, and wrote the opening lines of a cosmic story that would one day give rise to consciousness capable of wondering about its origins. So as you drift in the quiet of this moment, perhaps lying still as if floating in the void itself, imagine that ancient night. A universe vast, cold, and waiting. Then in one forgotten corner a single giant star caught fire. Then another, then thousands, until the darkness grew soft with light. That first starlight still travels through the cosmos, still threads the silence, and in a quiet way, still arrives inside you as understanding. We are As many scientists and poets alike have said, a way for the universe to know itself. And when we ask how the first stars formed, how they reionized the darkness, how they seeded the chemistry of life, we are really asking a gentler question. When the first stars began to burn, did the universe feel itself awaken? What if the universe is not a random sprinkle of galaxies in the dark, but a vast living tapestry woven along invisible rivers of gravity? When you look at the night sky, it feels like the stars are scattered without pattern, like grains of sand tossed by an absent-minded giant. Yet on the largest scales we can measure, the cosmos reveals something far more disciplined, far more mysterious. It is as if an unseen hand once drew filaments across the void, and along those filaments matter gathered, cooled, and lit up as galaxies and clusters. Cosmologists call this the cosmic web, a phrase that sounds poetic but is brutally literal. In 3 dimensions, matter traces out strands and nodes surrounding immense caverns of almost nothingness, like bright city lights connected by highways over dark countryside at night. Max Tegmark once remarked that the universe is not only stranger than we imagine, it is stranger than we can imagine. Nowhere is that more evident than in this discovery that the cosmos has a skeleton we cannot see, a framework made of dark matter guiding everything that shines. Dark matter is the quiet architect, the invisible engineer, present everywhere, announcing itself not by light, but by pull. Vera Rubin helped reveal its presence when galaxy rotation refused to obey the visible mass, as if each galaxy sat in a hidden halo of extra gravity. On the scale of the universe, those halos do not float in isolation. They are connected along long, cold streams of dark matter that collapsed first from the tiny ripples left in the afterglow of the Big Bang. Those ripples are still visible in the cosmic microwave background, frozen whispers from when the universe was only a few 100,000 years old, a baby still wrapped in its first light. From those primordial variations, dark matter began to fall together, slowly at first, then faster as gravity amplified every tiny imbalance. Imagine a mist of invisible particles, stretching across space, and wherever this mist was slightly denser, it pulled still more of itself inward, forming knots and strands. These were the first outlines of the cosmic web, sketched long before any star was born. Baryonic matter, the ordinary particles that make up gas, dust, planets, and you, did not lead this dance. It followed. Like fog settling in the valleys of a mountain range, baryons drifted into the gravitational ditches carved by dark matter, cooling and compressing until the first stars ignited. Computer simulations have become our modern crystal balls, letting us fast forward billions of years of cosmic evolution in a digital universe. In the Millennium Simulation and others like it, we start with a nearly smooth sea of matter seeded with tiny fluctuations measured from the sky. Then press play. As time flows in accelerated silence, threads of dark matter appear, knotting together into nodes that grow brighter in the rendering. When we add gas physics, those nodes kindle with model galaxies, glowing points that settle neatly along the same skeleton traced by the invisible component. Neil deGrasse Tyson likes to say that we are part of this universe. We are in this universe. But perhaps more important, the universe is in us. These simulations are a reminder that our atoms once rode these currents like leaves in a cosmic river. Observational astronomy then turns this digital prophecy into measured reality, mapping millions of galaxies across deep volumes of space. Projects such as the Sloan Digital Sky Survey revealed that when you chart each galaxy as a point, the result is not a random fog but a sprawling network of walls, filaments, and voids. The famous images of the cosmic web look uncannily like neurons in a brain, or the fine branching of roots beneath an ancient tree. It invites an almost irresistible metaphor, as if the universe itself were thinking, sending signals along luminous pathways where gravity and time conspire. Yet the science remains concrete. These patterns match what cold dark matter theory predicts with remarkable fidelity. Within the densest nodes, galaxy clusters form. Gigantic families of hundreds or thousands of galaxies bound together in a shared gravitational fate. Between them stretch filaments where smaller groups and solitary galaxies line up like beads on a cosmic string, while beyond lie the yawning voids. Regions so empty that crossing them would mean traveling for tens of millions of light years without encountering a major galaxy. Stephen Hawking once said that intelligence is the ability to adapt to change. On the scale of the cosmos, structure formation is the universe adapting to the slightest imbalance, turning faint quantum fluctuations into grand architecture. To analyze this is to marvel at a profound hierarchy, because the process is both simple and subtle. On one level, gravity is the only rule that matters. Mass attracts mass, and the rest is bookkeeping. On another level, the details of gas cooling, star formation, supernova feedback, and black hole outflows determine how brightly each node shines. When galaxies collide within these filaments, stars are stirred, gas is shocked, new generations of suns spark into being, and central black holes grow heavier. Each cluster becomes a laboratory where this complex astrophysical ecology plays out over billions of years. Commenting on this grand picture, we might say that the universe behaves like an artist who begins with a faint sketch, then layers complexity over time. The first lines are drawn by dark matter, sparse yet decisive, setting the composition. Baryonic matter arrives later with colors and textures, painting in stars, nebulae, planets, and eventually living beings who can look back at the canvas. There is a humility in realizing that our Milky Way is just one small brushstroke on a filament, tucked among countless others in an immense web that stretches beyond what we can currently observe. From a meditative perspective, lying under a dark sky and knowing this story changes the way the stars feel. They are no longer isolated pinpricks but visible nodes of an unseen network that cradles us across cosmic distances. The emptiness between them is not mere nothingness. It is the silent stage upon which this pattern emerges. When you breathe slowly and let that image sink in, you might sense a curious peace in the idea that chaos gave way to structure not by accident, but by the patient work of simple laws applied over deep time. Some researchers like George Smoot have compared studying the cosmic microwave background to reading the face of God. Whether or not one shares that metaphor, there is no doubt that tracing the growth of structure from those early ripples to the present web touches something spiritual in many minds. It suggests that the universe is not merely expanding, it is also unfolding, layering meaning as complexity arises. From quantum seeds to dark matter filaments, from filaments to galaxies, from galaxies to stars and planets. from planets to life and thought. There is a continuity that feels almost like a cosmic breath. In the end, when we say that dark matter leads and baryons gather along invisible ridges, we are really saying that our own existence is tied to structures we cannot directly perceive. Our atoms were once part of diffuse gas sliding along a filament, drawn into a forming galaxy, recycled through stars, scattered by supernovae, and gathered again in a quiet corner of a spiral arm. To learn how the cosmic web develops is to learn the secret migration history of everything we are. Perhaps that is why, even as we turn the mathematics into simulations and surveys, there remains a hush in the heart, a sense that in mapping these vast structures we are tracing the oldest paths that led from the first trembling light to the simple act of you listening now. Have you ever wondered why our sun is not the first star to shine? Why our solar system was born from the ashes of other suns, long dead and scattered across the galaxy? We orbit a gentle, yellow star, yet behind its calm face hides a violent ancestry, a story written in shattered worlds and exploded giants. When you look at your own hand, at the iron in your blood and the calcium in your bones, you are looking at the memory of ancient stars that died so that you could exist. As Carl Sagan once said, we are made of star stuff. But how exactly did that star stuff learn to breathe and to ask questions? The sun is what astronomers call a second-generation star, perhaps even third or more. That simple phrase carries a quiet revelation. It means there were older suns before ours, huge luminous beings that lit up the young galaxy, forged the heavy elements in their cores, and then died in titanic supernovae. Their deaths seeded the Milky Way with metals in the language of astronomy. Everything heavier than helium is called a metal. Stars like those were the true ancestors of Earth, not just poetic ancestors, but literal chemical parents. Neil deGrasse Tyson once remarked that the universe is under no obligation to make sense to you. Yet in the quiet logic of stellar evolution, there is a strange tenderness. Older stars give their bodies to the galaxy, so that later stars can be born with richer ingredients. In the distant past, long before the sun existed, the region of the Milky Way we now call home was a dark, turbulent cloud of gas and dust. Gravity was the patient artist, slowly gathering this material into dense knots. Somewhere in that cloud, perhaps nudged by the shockwave of a nearby supernova, a particular region began to collapse in on itself. As the gas fell inward, it heated up, spun faster, and flattened into a disk around a growing central sphere of fire. That growing sphere would become our sun, and the swirling disk would become the nursery of planets. Astrophysicist Kip Thorne once compared gravity to a master choreographer, curving space and time to guide the dance of matter. In the solar nebula, this choreography was everywhere. Microscopic grains of dust collided gently, stuck together, grew into pebbles, then boulders, then mountain-sized planetesimals. Each collision was almost nothing, a whisper in the vastness. Yet over millions of years these whispers built worlds. The metals in those grains were not original to the universe. They were the ashes of elder suns, enriched with carbon, oxygen, silicon, iron. Every grain carried a tiny fragment of past thermonuclear furnaces. One could say the solar system is a work of cosmic recycling. material once locked in the heart of red giants, once blasted outward in supernova storms, was gathered again into cooler clouds, then collapsed to form new stars and planets. Astrophysicist Maria Zuba wrote that planets are fossils of the formation process. The rocky bodies in our system preserve in their composition and structure the stages of this journey. Mercury with its oversized iron core, Mars with its frozen deserts, the asteroids with their raw, unmixed material. All of them are pages from the same ancient book. As the young sun ignited nuclear fusion in its core, it began to shine with a steady light, sending out a fierce wind of charged particles. This solar wind swept the inner disk, blowing away much of the remaining gas, leaving behind mostly rock and metal close to the star. That is why the inner planets are small and dense, while the giants farther out could gather thick envelopes of hydrogen and helium. Planetary scientist Sarah Seeger often reminds us that planetary systems are shaped by both violence and serenity. Calm orbits today hide a history of collisions and migrations. On the scale of human life, this process is beyond slow. In the language of the cosmos, it is almost hurried. In just a few tens of millions of years, the main architecture of our system emerged. A small, rocky world at the third orbit found itself blessed with a moderate distance from the Sun, neither too hot nor too cold. It inherited water delivered by icy planetesimals, and a mix of elements assembled across stellar generations. The same heavy elements that once shone inside giant stars now cooled into oceans, crust, and atmosphere. Here the story becomes more intimate. Geophysicists tell us that Earth's iron core powers a magnetic field, shielding our atmosphere from the worst of the solar wind. That iron did not appear by magic. It condensed from a nebula rich in metals, itself fed by ancient supernovae. The carbon that would form the backbone of organic molecules was forged in red giant interiors through the delicate triple alpha process. The oxygen we breathe once blazed in stellar cores. Later, on the cool surface of a small blue planet, these atoms assembled into cells, into forests, into animals who look up at the sky and wonder. There is a quiet paradox here. The more precisely we study the physics of star and planet formation, the more the universe begins to resemble a tapestry of memory and inheritance. Nothing is truly new, and yet everything feels unprecedented. Astrophysicist Martin Rees has said that the universe is comprehensible and yet weird. The solar system is a clear example. Its formation follows the laws of gravity, thermodynamics, and nuclear physics. But the outcome of those laws is a tiny world where poetry is written about galaxies and where beings dare to model the first seconds after the Big Bang. When we speak of metals increasing with each stellar generation, we are also speaking of possibilities increasing. The first stars had almost only hydrogen and helium. They could not build rocky planets like Earth, nor complex chemistry like ours. As generations passed, the galaxy gradually enriched itself, like a painter adding more colors to a palette. By the time our sun was born, the Milky Way had enough metallicity to craft a planetary system with terrestrial worlds, icy moons, ringed giants, and countless small bodies. Somewhere within that variety, evolution found a path to consciousness. So when we say the solar system formed from recycled matter, we are not diminishing its uniqueness. We are acknowledging that we belong to a lineage stretching back to the first light in the universe. Our story only makes sense inside that larger story. The Big Bang gave the universe hydrogen, helium, and the seed of expansion. The first stars gave it metals, color, and complexity. Later generations gave it planets, climates, oceans. Finally, on at least one world, the universe gave itself the ability to ask why. Imagine for a moment that you could gather every atom in your body and trace it back through time. The oxygen in your lungs might lead you to a red giant star in a forgotten spiral arm. The iron in your blood to a supernova that exploded before the sun was born. The silicon in your bones to a dusty nebula drifting in the newborn Milky Way. Each atom has traveled billions of years to be here now, arranged into a pattern that can listen to these words. In this sense, the formation of the solar system is not just an astronomical event, it is a chapter in our own biography. Without elder stars enriching space with metals, there would be no Earth, no continents, no seas, no minds capable of watching the night sky in quiet awe. The great astrophysicist Subramanian Chandrasekhar once reflected that the pursuit of science is also a pursuit of a certain spiritual understanding. When we learn how our system formed, we are not only mapping trajectories and temperatures, we are learning where our story fits within the unfolding universe. So the next time you stand under a clear night sky, breathing slowly, feeling as if you are floating between the stars, remember this. The light that falls on your face comes from a star that is a child of many suns, and you are a child of that star. The solar system is not an isolated miracle. It is a verse in a long cosmic poem, written in hydrogen, edited by supernovae, whispered by gravity. And as you drift towards sleep, you might quietly ask yourself, in this vast chain of recycled starlight, what new stories are still waiting to be born from the dust of our own fading sun? What if everything we have learned about the birth of the cosmos is not an ending to the story but only the first whisper of a much older tale? We look back to that primordial blaze we call the Big Bang, and we begin to see a pattern emerging from the haze. A journey from formless chaos to structure, from seething radiation to galaxies, stars, planets, and finally to the quiet miracle of life wondering about its own origin. In the first instance, the universe was a storm of pure energy, a sea without shore or shape. Yet hidden in that apparent disorder were the laws that would sculpt everything to come. Gravity began its slow dance, pulling matter into clumps, then clouds, then stars that lit up the darkness like ancient temples in a desert of night. As those stars were born and died, they forged in their hearts the elements that would become oceans and mountains and the fragile chemistry of thought itself. From that perspective, the universe is not only expanding in space, it is unfolding in complexity and awareness. Albert Einstein once remarked that the most incomprehensible thing about the universe is that it is comprehensible, and this is perhaps the deepest clue we have. Out of a fireball that knew no forms, minds have emerged that can write equations for that fireball, build telescopes to capture its afterglow, and feel awe in the face of its silence. Carl Sagan said, "We are a way for the cosmos to know itself." If that is true, then the narrative from Big Bang to human consciousness is not an accident scribbled in the margins. It is the universe gradually turning its gaze inward, discovering that the cold sky is capable of tenderness and reflection through us. Yet, even as our models become more precise, a question quietly lingers at the edge of every theory. Is the Big Bang the absolute beginning of everything, or only the latest verse in an endless cosmic poem? Some theorists imagine cycles of expansion and contraction, universes budding from quantum foam, or black holes giving birth to new realms beyond our sight. None of these ideas are proven. Yet their very existence reminds us that our understanding is provisional, a lantern rather than a sunrise. And so we arrive at a strange kind of wisdom. From the evidence we can say that, after the Big Bang, the universe cooled. Structures formed. Stars ignited. Worlds condensed. And life arose to ask questions about it all. But whether this grand sequence is a one-time event or a chapter in a larger and perhaps eternal cycle remains an open door. As we drift together through the dark on this small world, listening to the echo of that first explosion in the cosmic microwave background, we may feel both very small and strangely essential. Perhaps to understand what happened after the Big Bang is also to sense that the story is still being written through every thought we have, and every quiet breath we take under the ancient light of the stars.